So I hear you had a good day today. Lots of exciting stuff. Just thinking back, how many times did you interact with the national grid today? Can you think? A lot. Okay, yeah. But we take it totally for granted. We expect it is there and it works 100% of the time, always in the background, entirely dependable. And largely to date it has been, okay? So this morning we really looked at the current state and how we got there and how it works. What I want to cover a little bit this afternoon is what do we have to think about going forward? What is going to change? Why does it have to change? And what are the, I guess, the technical, the social and the economic challenges that are coming with that? So I want to cover a couple of different topics, things like electric vehicles, smart energy storage. Very briefly, I'm going to mention the Internet of Energy Things and community energy networks, okay? But not evenly spread. I'll be spending more time in some than others. So in terms of future grids, what is actually driving the change? Why do we have to change? Well, we know we need to decarbonise power generation. That basically means moving away from fossil fuels like coal, oil and gas. We have to reduce carbon. We can't successfully capture carbon yet and bury it. And my gut feel as a chemist is that it will never work economically in the long term. Okay? The process challenges are just too great. The expense will be too high and the alternatives are going to be more attractive. So we're going to move from dispatchable fuel sources, in other words, power that can be generated by sending a signal to a generator to burn more coal or burn more gas. We're going away from that to stochastic renewable sources. And these are sources of electricity mainly that have a probability distribution of being available when you need them. And we know from solar and wind that there is this inherent variability and we can't be absolutely certain that the energy will be provided when we need it. But we also know that if we don't match the supply of energy with the need, then we're going to have problems. And the problems can be as severe as the grid collapsing because the frequency shifts and everyone goes into a blackout mode. So that's one of the reasons, the decarbonisation. And actually I think, personally, and it's really just my opinion based on a few decades of following the literature, is that we're going to have to do this faster than most people appreciate. Okay? It's not, yes, by 2050 we can be 50 to 80% renewables. I think we're going to have to do it faster. And the faster that happens, the more difficult it is for planners and politicians actually to come to grips with it. Then they start to panic and make silly planning decisions, okay? And we all end up paying more for our power, which is what's happening now. The second point is that there is a large-scale uptake of solar energy, especially in countries like Australia. We've got such fantastic solar resources. The panel prices are becoming very much cheaper. And so people are quite happy to install solar panels. And why wouldn't you? It's quiet, it's clean, there's no moving parts, it doesn't emit odours, it doesn't leave waste products every day after it produces its electricity. So it's a pretty nice way of generating electricity. And it's becoming reliable and people are quite happy now to spend the money and put solar panels on their roofs. So there is this large uptake already happening. We're likely to see a strong uptake of electric vehicles for a number of reasons, and we'll cover one or two of those too. It hasn't happened yet, but it could be very soon, or it could be 10 years away. We don't know. And this is one of the very interesting aspects of future grids, the amount of uncertainty. It's huge. And if you're an investor or a government that's looking to find $20 billion to put into a power system, you pretty well want to make sure that you've got a reasonably good idea of what's happening.
Just going to turn you up.
Turn me up, okay.
Thank you. Make it really boom and project it.
Right, okay. And the availability of low-cost sensor, control and communications devices. We all have, most of us have them in our pocket already. The rate of change in the ability of, and the dropping of the cost of small-scale sensors and communication devices is phenomenal. You can now, for $10, buy a chip that will measure your electric power usage with a Wi-Fi connection that can load it into the grid. So I can go online now and I can tell you exactly how much our farm that Chris mentioned before, how much electricity it's using now, even though it's 400 kilometres away. The cost of those things has come down to almost nothing. Affordable battery storage systems, we'll spend some time on that, as well as the whole issue of sustainability and affordability. We've got to a situation with the current system that it's actually becoming unaffordable to a lot of people. Okay? So these are all part of the drivers of change as to why the future grid's going to change. So how is it going to look different, I guess, from an elevated level? On the left-hand side is the traditional grid model, where we have in the centre these large-scale remote power stations. They could be nuclear, coal, hydroelectric, and from there power flows out. It flows out along the transmission lines like water in a pipes down to where it's needed. That's the conventional power system. What we think is going to happen in the future is we're going to have a lot more distributed systems, power systems within power systems, located either in houses or in commercial buildings or in big cities, spread across the landscape. There's going to be solar, there's going to be wind, there'll be other renewables that will be dispatching into that power system when it can deliver power, and the loads are going to be taking power out of the system when we need it. So it's going to be very much a different system. We're moving away from the very large one-way power flow model down to two-way power flows, systems that need to know what the other parts of the systems are doing. Hence this need to communicate, to understand what the load is doing, what the generators are doing, what the weather is doing. So this is a possibility for what the future grid is going to look like. So there's been a couple of studies, well, in Australia and around the world, on what is it likely to be. And again, the issue is with this uncertainty. We actually don't know, because there's lots of different pathways that the industry could go, depending on government policy, the cost of equipment, the cost of fuels, the way people use and interact with electricity. So we don't actually really know. But the CSIRO, which is one of the Australian Federal Government Research Organisation, undertook a very extensive consultative study a couple of years ago, speaking to stakeholders, the industry, people, households, government, saying, well, if the power system evolved in this way, what would that mean to you? And if it evolved this way, what did that mean to you? And so, without coming up with a prediction, they came up with some scenarios. And this is one way of dealing with this massive uncertainty, in that we don't know enough to actually make a confident prediction about where the future is going to end up. So they looked at 4 scenarios, and these are the 4 here. They split them up into one scenario which is basically called set and forget. So these are the people who are quite happy to let someone else manage their power and energy systems. As long as it's not too expensive, someone will reach in and make sure that their systems work properly, and they'll just pay the bills. Okay? A little bit like what most of us do today. You assume it's being managed properly. Another scenario was that if solar power and batteries become cheap enough, some fraction of homes, for example, households, will make a decision to leave the grid. We've got enough solar power, we've got enough batteries, we don't need a connection to the grid, we're going to leave the grid. And that looked at, about a third or so of customers just disconnecting from the grid altogether. That was another possible scenario. The third one they called the rise of the prosumer. And this is the producer-consumer. So these are households and business that both buy electricity and sell electricity. They have sufficient, for example, solar panels or some other renewable source, and when they have excess, they'll sell it back to the grid, and when they don't have enough, they buy from the grid. Okay, so that was a scenario. And the fourth one was this renewables thrive, and this is basically the largest system where most of the large-scale coal and gas-fired power stations are replaced with renewables. So this is large-scale solar thermal, large-scale solar PV, hydroelectricity, wind, waves, all the renewables. So they looked at those 4 scenarios and said, well, what does that mean for planning? What should we be looking at and thinking about today so that in 10 years' time, 20 years' time, 30 years' time, we don't find ourselves in a situation where we don't have a stable electricity supply, or it's so expensive that a big fraction of the population can't afford it, or industry has abandoned Australia because power prices are too high. So they looked at those four scenarios, came up with very, very interesting solutions. They're not predictions, they're just what-ifs. What if this happens, then this will happen. Okay? So none of them, you wouldn't put your hand on your heart and say, yes, I believe leaving the grid is going to be, the most likely scenario. It might be, but no one will know until it happens. Okay, so let's have a look at some of the things that are going to influence future power systems. Well, one of them we know is going to be electric vehicles. Okay? Currently, not much uptake, countries like Australia, although in the Northern Hemisphere, in Norway, for example, 20% I think of new vehicles sold are all electric. So they are likely to grow, but how quickly? How many are going to be employed and used? And electric vehicles are going to strongly affect how power systems need to operate. But if we go back and just look at some history, it's eye-opening as to why we ended up with what we have today and not electric. 110, 115 years ago, there were more electric cars than petrol cars on the road. Okay? Ferdinand Porsche designed an electric and a hybrid car. Okay? And in those days, there were more electrics, as I say, than petrol. But what happened was the discovery of cheap oil. And when cheap oil became available, the internal combustion engine became much, much more economical and practical to use than electric vehicles. So electric vehicles died away very quickly. And basically not much happened for 80 or 90 years until one of the oil crises, I think the second oil crisis, in about late 1980s, mid-80s, people started to think, gee, we can't rely on cheap oil anymore, so let's go back and look at electric vehicles. And there was a surge. There was the GM concept electric vehicle, and there's even been a documentary made as to why it was scrapped by GM. Okay. But today what we're seeing is electric vehicles are coming back in interest for a number of reasons. Firstly, the technology is becoming reliable, the batteries are becoming affordable, the cars are still a bit expensive. You might pay double for an electric vehicle than you would for a conventional mass-produced internal combustion engine, but some people are willing to do that. So in terms of electric vehicles, obviously you need to carry some energy with you to make it go. How much energy do you need in an electric vehicle? Depends on a lot of things. It depends on how many kilometres you want to travel before you have to stop and recharge it. Okay? And remember, recharging an electric vehicle is a lot slower than recharging with a chemical fuel. You can put a huge amount of energy into a fuel tank through liquid fuel very quickly, in as much time as it takes to fill up your tank. It could be a minute. To recharge a battery takes a lot longer. So you want to make sure that you've got as much range as you can get in your electric vehicle. How efficient the electric motor is in the associated power system? Well, one of the very attractive things about electric vehicles is that they are not thermal engines. Okay? And remember, this morning we were talking about the Carnot efficiency limiting how much fuel to useful work you can get. Electric motors, being non-thermal, can be extremely efficient. And there are motors that have been designed and used that are 98% efficient. So 98% of the electrical energy that goes in is recovered in motion from the shaft. Okay? So they can be made extremely efficient because they don't have that Carnot limitation of extracting work from heat. Of course, it depends on the route as well. If there's lots of hills and if you want to race around, as people sometimes want to do, then you'll consume more energy from your battery than otherwise. Are you going to use air conditioning, power steering, the lights? All of these things are going to take energy from the battery. So how big a battery will you need will depend on lots of things. The two examples that I've got here is for the Tesla Model S, which is, the poster car of the electric vehicle fraternity. Very sporty, extremely well made, very desirable car, 85 kilowatt hours. That's their battery capacity. The much smaller BMW i3, 33 kilowatt hours. So thinking back to what we talked about this morning, you can see, or get in your mind, a feel for how much energy needs to be carried in the battery. Now don't get carried away with people saying, but you know, batteries will never contain the same amount of energy as a litre of petrol or a fuel tank of petrol. Technically, you could say that, but it's not actually true, because the fuel use, firstly, it's a one-off. Once it's burnt, it's gone. Secondly, its efficiency in being converted from fuel to motion is only about, in a car, only about 15 to 20%. It's much, much less than a big power station, because the engine is starting and stopping, it's not running very efficiently, so only about a fifth of that chemical energy in the fuel is actually used as motion, or gets through as motion. So yes, it takes a lot of batteries to move a car, but you're doing it much more energy efficiently, and the battery can be recharged day after day after day. So the comparison between fuel in the tank and energy in the battery is a little bit more complicated than some people believe. This is a photo of the Tesla battery pack. Surprisingly, it's made up of thousands and thousands of small cells. They're called 18650s. You know, they're approximately that size. And you might think, well, why on earth have they gone down this route? Well, they started and they continue down this route because the manufacture of those batteries has been undertaken in mass production for a number of years, and their characteristics, their reliability, very well known. The failure rate is measured in parts per million, so factory producing 10,000 of these cells a day can be pretty sure that very, very few of them are actually going to fail quality control. So there's 7,104 cells in 16 modules of 440 cells each. Okay? And that's how they connect it up. And they sit in the base of the car. And if you've ever had a look inside a Tesla, you open the bonnet, there's nothing there. You open the boot, there's almost nothing there. The entire power system is really sitting under the cabin. Now, in terms of connecting electric vehicles to the grid, this is like a whole new industry or a whole new electrical load having to be supplied by the grid. And we know already that it's imperative that the supply always meets demand. So if there's going to be a lot more electricity required, we better know when it's going to be needed and how much that's going to be. So people are looking around and saying, okay, well, how many kilowatt hours are actually going to be used by a vehicle? How much is going to have to be provided by the grid when the vehicle is recharged? So for comparison, we can have a look here. There are two vehicles that I've compared. One is the Nissan Leaf, which is a smaller, more modest vehicle compared to the Tesla. And the electricity or the energy consumption per kilowatt or per kilometre is 173 watt hours per kilometre. So instead of litres per 100 kilometres, we're now talking about watt hours per kilometre, and the Tesla's 200. So if you're travelling 5,000 kilometres a year, which is not a lot really, 100 kilometres a week. If you're travelling 5,000, then over the year the Leaf is going to need about 865 kilowatt hours of electricity, and the Tesla about a megawatt hour of electricity, 1,000 kilowatt hours. If you're doing a lot more, obviously it goes up in proportion. So if we looked here at 15,000 kilometres, which is a little bit more realistic for certainly driving in Australia and the US, for example, the annual electricity average for a Sydney home is about 5,700 kilowatt hours. So we can see that the addition of an electric vehicle to a home and used for that amount of kilometres, it's going to be about a 50% increase in the amount of electricity that home is going to need. And 50% increase in the amount of electricity from homes is quite large. Now, if there's only 1 in 100 homes has an electric vehicle, it's not a problem. If 95 of 100 homes have electric vehicles, then it becomes a problem. So this has to be incorporated into the modelling to see what effects electric vehicles are going to have on the system. And one of the problems that can happen if it's not planned properly is that if everyone has their electric vehicle They drive home from work or from wherever they are, they go home and they plug it into recharge. Recharging the electric vehicle is going to massively create a demand for electricity at that time. And we know that, again, supply must meet demand, people have to anticipate, the generators must be prepared. So doing things like this, where everyone has uncontrolled ability to charge their electric vehicle, could black out a system. So the policymakers and the planners have to work out what is the most stable way of allowing people to charge their electric vehicles. And you can't sort of dictate to people, you can't connect your electric vehicle to your power point to charge up until 2 a.m. in the morning, because some people might say, look, I leave home at 4 in the morning, I have to drive somewhere else, I'm going to charge my vehicle when I want to. So the way to control this is to adjust the tariffs for electricity to encourage people into behaviour that doesn't cause massive demand on the grid at any particular time. And so this is where the financial part of it needs to be managed as well. So governments, planners, retailers, energy providers have to work out what is the best time for people to recharge their cars if there's going to be a lot of electric vehicles, and then how to encourage them to do that. People think, and probably will happen, if you've got a lot of PV on the roof at your home, then you could charge up your electric vehicle. But if your electric vehicle is at work and no one is at home, then you can't charge your electric vehicle from your PV panels, but you could charge it at work. So your employer might provide a plug-in charger, and that could become part of your salary package, that you get free electricity from your university employer or your industry or somewhere else. All of these things have to be worked through. How many electric vehicles are going to be taken up depends on a lot of things. It depends on the price of electric vehicles, and up till now they've been quite expensive, generally out of reach of most working, modestly wealthy people, but the prices are coming down very quickly. And I heard just the other day that the new Tesla smaller model is going to be, the production is starting later this year, and their target price is, to be comparable to an internal combustion engine vehicle of the same size. So the prices are coming down, battery prices are coming down with it. Another big driver, certainly in countries like Australia and the US, is the price of oil. Whenever the oil price spikes up, people think, time to move away, next car will be an electric vehicle. The price of oil is unreliable, it's too expensive, and it turns out it's actually a lot cheaper to run an electric vehicle on electricity than it is oil, for a number of reasons, but the main one is, for every unit of electricity that you pay for, most of that ends up moving the car, whereas in your petrol, only about a fifth of what you pay for actually moves the car. The rest goes into heating up the atmosphere and the planet. Consumer awareness of this value proposition will change, and government incentives. Some countries incentivise people to buy electric vehicles by reducing registration tax and insurance or other things that they can do. So over time, we expect it'll become more and more attractive for people to think about buying electric vehicles. This is just a chart of the oil price going back a quarter of a century and a bit, and you can see there's been lots of very, very high prices, and currently, we are sitting down at about $50 a barrel. Where it's going to go, no one knows, basically. If there is some conflict in the Middle East or some other part of the world, it's quite possible oil prices will skyrocket again, or it's possible that they'll collapse. We just don't know. So these are the uncertainties. How do you plan for and design a system when you have really no idea as to what things are going to be like in 10 or 20 years' time? Okay, so moving on from electric vehicles, and I guess the connection is electric vehicles have batteries. Batteries can also be used in a stationary mode at a home or a power station or somewhere else. And it's basically the same technology. The same battery that goes into the Tesla car is actually used in the Tesla Powerwall. Okay? It's the same. They're starting to make a slightly bigger cell, but it's basically the same thing. So if electric vehicles have encouraged the mass manufacture of batteries for cars, stationary battery use for homes and businesses is benefiting, because the more you produce these batteries, the lower the unit cost becomes. So not only is it benefiting transport, but it's benefiting stationary storage as well. Now, batteries aren't the only way of storing energy. There's some good reasons why we love them. Not everyone, but I mean, we've all had the experience of flat laptop batteries and flat phone batteries. But they're doing a tough job. The battery in your phone is really doing a lot of work. And it's a small battery because no one wants to carry around a big brick. And with all the smarter systems that are involved now, they're basically a computer in your phone, it does put a lot of strain on the battery. But look, there are so many different types of energy storage. There's mechanical storage, which could be like pumped water, pumped hydro, thermal energy storage, where you can store energy in heat, hot water, molten salt, electrical, electrochemical, chemical. There's lots of different ways of storing energy. But we're not going to really go through all of them. So what do electricity grids need or want from energy storage? Well, firstly, if you're going to apply storage at a national grid level, you need the ability to store really big leaks of energy, okay? And enough to make a difference to the grid, so you're talking about hundreds of megawatt hours. So remember, the Tesla S battery was 85 kilowatt hours. So we're saying now that we need hundreds of megawatt hours to be useful in a grid. It doesn't have to be all in one place. It can be spread out, but if its storage is going to be used, then we are talking about hundreds and potentially thousands of megawatt hours. They need to charge and discharge quickly. And generally, from analysis that we've done and other people have done, you want to be able to charge and discharge this battery in an hour or less. Okay? Some batteries can be charged very quickly, other batteries take a long time to charge, and it depends on the chemistry. So the lead-acid battery that people are familiar with in their car, which starts the car, really shouldn't be charged or discharged any faster than over 20 hours. So when you start the car, a little bit of current is taken from the battery, but it mostly stays full. And if you've completely flattened your battery, as some of you might have done, you might notice that their lifetime collapses. So what might have lasted 5 years, if you fully discharge your car battery, you might find that within 12 months it's no longer able to start the car. That's because the chemistry is not designed to move electrons in and out really quickly. You need a long lifetime for this sort of storage, at least 10 years. No one's going to spend a huge amount of money on a battery that lasts 50 weeks. Okay? So the lifetime has to be there. The chemistry, the manufacture has to be robust. It has to be low cost. It has to be a better economic proposition than burning gas in a gas-fired power plant. Okay? Because if you need energy and the sun's not shining, the wind's not there, your option is you store energy somehow and then use it, or you turn on a gas plant. So if the gas is cheap, then batteries are not going to be that economic. So it has to be low cost. It has to be safe and efficient and a whole lot of other things. Now, this is a pretty big ask for a modestly new chemistry. Batteries have been around a long time, but to manage these sorts of requirements, really only the last decade or so. Okay, so very quick run through the different types of energy storage, but I'm not going to dwell on them. Big capacitors, high specific power capacitors, which stores energy by separating charge on two electrodes. There's no chemistry in a capacitor. If there is, then it's going to fail. So capacitors are really good at moving energy in and out quickly, but they don't store much, maybe a tenth of a battery. Okay? So supercapacitors, and they are already being used in different places. Underground compressed air is being used, surprisingly, already. There's a couple of plants. There's a big plant in Germany, a big plant in the USA. They pump air into underground chambers when there is a lot of spare electricity, and then when it's needed to meet a peak load, the air is exhausted and run through a gas turbine to generate electricity. So underground compressed air actually makes a lot of sense for really big energy storage, grid-connected, remote at a power station, but it depends on the geology. You have to have underground caverns, basically, where you can pump that air and store it. So if it's an old salt mine, for example, it can work. That's just a photo of the Huntorf compressed energy storage plant in Alabama that is running adjacent to a wind farm. So it works. It's not something that you can build quickly or move around, but it does work. And it acts like a battery, but a battery over many, many hours. Pumped hydro we know of. Most people here are familiar with that. You pump water up to a reservoir when you've got excess energy or cheap energy. Then you let it run back down through the turbine when you want it back, generate your electricity. If you've got access to the sea, that's even better because you can use the sea as the low reservoir. Now, pumped hydro is actually the cheapest form of energy storage currently available. It's miles cheaper than batteries. Okay? So why don't we use more pumped hydro? In countries like Australia, it's really difficult actually to find a good site where you can do that. There are some photos here of artificially built reservoirs that are close to the ocean. We don't have that many places in Australia where you can do this. Most of the population lives on the coast. Being able to do this anywhere near a population centre in Australia is pretty challenging. So lack of sites for countries like us and other countries that don't have a lot of water is a problem. It's relatively low energy density. In other words, the amount of energy you can store per volume is quite low. And you can't put it really next to the load. It has to be far away. Typically, it's far away. And so there's always losses associated with it getting the energy from where it's generated to where it's stored and to where it's needed. May have to go through hundreds of kilometres of power lines. So there is definitely a role for it, but it's unlikely to dominate in countries like Australia. Flywheels, another way of storing energy. They have already been used in grid systems for rapidly injecting power and absorbing power to try and keep that frequency stable. So there's quite a few installations around the world, largely in the USA, where there are banks of flywheels operating, buried underground actually, that respond to the changes in frequency maybe 25 times an hour. Okay? So they are there keeping that stability, a bit like a shock absorber in the system. Again, very high power, they can move energy in and out quickly, but don't store too much, okay, because it's the stored energy in the spinning flywheel. Superconducting magnetic energy storage. This is storing energy in a magnetic field. And when you have a superconducting magnet system, then you get a very intense magnetic field and you can store a lot of energy in it. And about 10, 15 years ago, it was seen or thought to be the breakthrough technology. We use them all the time in magnetic resonance imaging, the MRI. It's a superconducting magnet, kept very, very low temperatures with liquid helium. There's an intense amount of energy that you can store in that electric and magnetic field in the coil. But it turns out in practice it's really difficult to make these things cheap and reliable. You have to have a cryogenic system to keep the low temperature. There's lots of power conversion going into and out of these systems, and they've been a bit of a disappointment. So I can't see that superconducting magnetic energy storage is going to make any breakthrough in the near future. Which brings us to batteries. Batteries are sophisticated chemical machines, sensitive chemical machines. We take them for granted, but inside there is a lot of chemistry going on. And there's lots of different types of batteries. Most people are familiar with the old lead-acid battery system that's in most people's cars, and it's there because it's cheap. It doesn't have to do much. It has to start the engine occasionally, provide a little bit of power to the radio or the stereo when you're not running, but generally doesn't do much. It can be used for stationary energy storage, for homes, for businesses, for example. It's got some limitations, but some of the advantages too. It's quite low cost. It's understandable. People are comfortable and familiar with it. The big chemistry at the moment and for the foreseeable future is lithium-ion batteries. And a lot of development has gone into those because you get a lot of stored energy per unit mass and volume. So they're very high in specific energy and very high in specific power and energy density. So a small battery can store a lot of charge. But there's lots and lots of different lithium battery chemistries. There's at least 18 different lithium battery chemistries. And everyone's phone and everyone's laptop doesn't necessarily have the same chemistry. It depends on the manufacturer and the specifications. There are things called flow batteries, which are like a chemical, like a fuel cell, where you're flowing electrolyte over a system of electrodes that you can then store electric charge. And these are things like zinc bromine, and there's a manufacturer developer in Australia called Redflow. There's another developer in the USA. These are batteries designed for long life and stationary use with very low potential cost. Nickel-ion batteries, this was the battery that Thomas Edison invented and is still around, and it's still used, although it's not that popular, but it's still used because it's robust. It doesn't break. No matter what you do, you can't kill this battery. We know that it's easy to kill a lithium-ion battery. You overuse it and its capacity will fade away. You completely discharge a lead-acid battery and it'll fail. You can't do that with a nickel-ion battery, but it's got a whole suite of negatives. It generates a lot of hydrogen. It's not very efficient. So for every 100 units of energy that you put in, you may only get 50 out. Okay? And the rest has gone into heat and generating hydrogen. But very, very robust. There are high-temperature batteries. These are used industrially, commercially, the sodium-sulfur battery. Liquid metal batteries developed in MIT. Aluminium-air batteries, sodium batteries, all sorts of batteries coming out now, all with different chemistries, different advantages and disadvantages. So the properties of batteries, how do you specify them? How do you know that they'll do something, for example, in a car or connected to a power grid? Well, there's a couple of things to keep in mind. First is what's called the C rate, and this is how fast it can be charged or discharged. So the C rate, a 1 hour battery, with a battery with a C rate of 1, means you can fully charge it or fully discharge it in 1 hour. You can take longer if you want, but you can't go faster. Okay? A lead-acid battery might have a C rate of 0.1, so it takes 10 hours to charge and discharge. Okay? So it's not a fast battery. The chemistry is such that you can't move the electrons and the charges in and out very quickly. Then there's specific energy, specific power. We mentioned before, this is energy per unit mass and energy per unit, or power per unit mass, and also per unit volume. So for an electric vehicle, you can't afford to have a very low specific energy battery like a lead-acid battery, because you end up just having a truck full of batteries that also happens to have a driver, because you need 1,000 or 2,000 kilograms of battery to get you 100 kilometres. So for electric vehicles, very high specific energy, very high specific power, which means lithium currently. Depth of discharge, how fast or how far can you discharge the battery? Can you discharge it completely flat? Many batteries don't respond well to complete discharge. And it's because of the chemistry of the materials on the electrodes. A charged electrode and a discharged electrode have a different chemical structure. And very often, it's a completely different phase of material that will have to expand or contract depending on whether it's charged or discharged. And so it's this change in shape and volume during charging and discharging that slowly eats away and breaks down the material. So some batteries will be specified not to be discharged below 30%. So fully charged 100%, you're not to discharge below 30, because every discharge below that is going to weaken the electrodes and affect the battery life. So depth of discharge is important, and of course the cost, which is associated with the lifetime. How many cycles can you charge and discharge this thing? Toshiba make a battery, the lithium titanate, and they claim 20,000 cycles at 80% depth of discharge. So that's 50 years at 1 cycle a day. You might say, well, why aren't people using these batteries in everything? Well, because they probably cost 10 times more than the competition. But it can be done. They're very efficient, 98% round-trip efficiency. Every 100 units of electricity that you put in, you can get 98 out, which is pretty good. So the losses are very low. And they discharge and charge very quickly. An 8C rate. So they can be charged and discharged in about 8 minutes. Okay? And that's very good for things like electric vehicles. You want to be able to charge them quickly, you want to be able to discharge them to get that power out. And so it's really been the push to develop better batteries for electric vehicles that the electricity infrastructure industry is benefiting from. And there was an article in Nature, the famous scientific journal, about 18 months, 2 years ago, and the question was asked, will Tesla's battery change the energy market? The market that we're talking about here, the power market. And I think the answer was yes, it will. And we've recently seen them come out with a new pricing structure for their stationary batteries, which has made it even more attractive to people who want to install batteries and photovoltaic panels on their homes or their businesses. So one industry has been driving performance and cost for vehicles, and the stationary industry is benefiting from that. Yeah, falling costs for battery packs is one of the drivers for this. And of course, Tesla are building this massive factory. It's eye-watering as to actually how big it is. The capacity of that factory when it is producing in full production, is massively increasing the amount of energy storage that will be available not only for electric vehicles but for stationary power grid use as well. So this is a technology driver that's going to change the infrastructure that we use every day for electricity generation. It's not coming about because governments are making policies or planners are doing something else. It's coming about because industry is developing a better product that people will want to introduce and use in their electricity supply systems. Okay, so moving away from electric vehicles, how am I going for time, Chris? Okay. Yep. So now we move away from electric vehicles. Let's talk about energy storage at the house, at the home. Okay, this is really integral now with power systems. And we know, or we see, that the combination of photovoltaic, solar panels and energy storage is becoming very compelling for lots of people. They're looking at their electricity bills, they're very unhappy, they've gone up a lot, they've got solar power on the roof, which they're very happy with, and I think, gee, if we can just store what we don't use during the day, we won't get such huge bills because of our peak demand later in the day or at night. So that's a compelling vision for a lot of people. Storage at the household level can be economic in some cases, and we've done lots of simulations and modelling on this, but it is really dependent on the way that the electricity is used in that house and how much you pay for it. There are time of use tariffs that you pay for different times of the day. Some people can benefit from those, others prefer not to have them, and they're not always made available. But if you're on a time of use tariff that says at night your electricity price is going to be a third of what it is between 2 p.m. and 8 p.m, then it behoves you to start thinking about trying to use as much of your solar power as you can for those 2 p.m. to 8 p.m. periods, because that's when you're paying the most for your electricity. So it depends on your pattern of usage. Is everyone out during the day so that there's not much usage in the middle of the day, or are people home all the time? Is it a big family, a small family, a single home family? It all depends on the profile of electricity consumption as to whether it'd be sensible or not to invest in that. So how do planners determine the medium and the long-term effects of energy storage and PV uptake? We can see, well, the planners can see that people are attracted to these things, but how many people are going to buy them this year, next year, the year after? What is industry going to come and provide for people to make it even more attractive for them to do it? Planners need to know this, but it's a guess at the moment. And last night there was a big event in Sydney where a major German battery manufacturer launch their new product, and their new product is, if you buy our battery and you already have solar on your roof, you won't have to pay for your electricity again. Sounds pretty good, doesn't it? Now, there's obviously lots of ifs and buts in there, but what they're saying is, you buy our battery, you let us use it when occasionally we need it, and we will charge you something like $30 a month flat fee, no matter how much electricity you use. Sounds like a pretty good deal. Now, they're doing this because they know that if they have a large number of storage batteries connected in the network, they can then use that stored capacity to sell that capability back to the utilities. Like we were talking before, there are services that people pay for to keep the frequency stable, to keep the voltage stable, to ramp up and ramp down the supply of energy so that it meets the load. If you aggregate people's batteries together, then you can play in that market. So these organisations are saying, we'll use your battery, and in return, you can have almost free electricity. And they've done the numbers, so they know that they'll come out ahead. So these sorts of economic and financial packages are also going to influence the, I guess, the topography of the future grid. So we need to have mathematical models so we can understand these flows of energy. Where is the energy going to come from? Is it going to be stored at the homes? Is it going to be stored at businesses? Is it going to be stored in a hydroelectric dam 100, 200 kilometres away? So we need models to understand how that's going to happen. For example, at what state of charge should the battery be at the start of the day? Okay, so if you've got a battery system at home and a PV panel, the best value you'll get out of that battery is if you know how much energy you'll need that day and that night, and how much energy is going to come from your solar panel tomorrow. Okay? Because if you know that tomorrow is going to be an overcast day and your PV panels are not going to generate much, then you'll want to make sure that your batteries are highly charged at the start of the day from an off-peak grid connection, because you can't rely on your PV for tomorrow. But you need to know that 24 hours in advance, or at least 12 hours in advance. So to get the optimum out of your PV and your storage, someone has to reach in and tell you what the PV output is going to be tomorrow, what your historical consumption is going to be, how that affects how much you pay for your electricity. And the average person in the household is not going to do that. So there is a growing base of services that people can now tap into that do that for you. They'll tell you that tomorrow it's likely that the solar output of your PV is going to be great, because we know the weather is going to be clear tomorrow, it's going to be cool, and we know exactly how much your PV is going to produce for every minute of the day. That goes into a mathematical model that comes back and tells the battery, you can be 3/4 discharged tomorrow morning, because during the day you're going to be charged by solar. So all of these systems are now becoming much, much more intelligent. They're talking to each other, they're going into the cloud, the computations are being done, the results are being sent back via the internet, and the system picks those up. And we already have here at the uni, we use it for our research purposes, we get a 72-hour solar forecast. What is the amount of solar energy that could be available here 3 days' time? And we use that as part of our models as well. So there's a growing need for this sophistication to manage the storage. The uncertainties, and there's lots of them. As I mentioned, customers are going to choose various technologies and sizes and not necessarily the optimum ones. So what a plan is to use is part of their decision-making tools. How much are we going to invest in poles and wires in 10 years, 15 years' time? Should we be trying to think about building another power station as the population grows? Are we going to use so much electric vehicles that we have to have a doubling of the amount of generation on a particular day of the year? All of these decisions have to be made years in advance. Because, for example, a new power station might take 5 years to get approval before the building starts. A nuclear power station can take 15 years from deciding to go ahead with it before the first electron comes out. And in 15 years' time, what are the power prices going to be? No one knows. So grid-level modelling requires consideration of a lot of these uncertainties, the stochastic nature of renewables energy systems. And so it becomes down to a problem of how do you deal with uncertainty in a mathematical sense. How do you make robust models that you can test different scenarios going out years and seeing what the effect is? And that's a lot of what we do here and in other places. We develop mathematical models to try and understand what the system would do if there are different pathways. And then the planners can look at that, and I think up till now have ignored it. But they can look at it and say, okay, if solar and batteries are going to be a big part, then in future we need to model a system where the energy flows are going to be two-way in the power lines that we've got already. They'll be going into your home for some hours of the day, they'll be coming out of your home for other hours of the day. And what does that mean for the infrastructure? I'll skip that. Let me go on to community energy networks now. So we looked at one home, for example, that has PV and storage, and there's some attraction there, there's a bit of cost. But very typically what we find is that over a group of homes, in a street for example, everyone's consumption, and if they have PV on the roof and their generation, is not the same. In general, yes, people use a little bit more in the mornings, less in the middle of the day, and more in the evenings. But you might be next door to a house that has a retired couple that's got no PV on their roof, but they have a battery. Okay? So the retired couple are going to be at home during the day. You might be out at work during the day, so your energy needs during the day are very low, but your PV system is generating its best in the middle of the day. So it would make sense for your energy to go to your neighbour who doesn't have PV and has a load during the day. And they can use that or store it and provide their battery stored energy to another neighbour. Or someone might be away on holidays for a week or two. Their energy generation and storage can be shared amongst their neighbours. So there's a very intriguing model of getting neighbours, and it works for businesses too, to generate and share their energy and their needs together. Now, at the moment, that's almost impossible to do in a market system like we have in Australia. You can't sell your power to a neighbour. Okay? It's against the law. Only licensed generators can sell electricity. So you can't do that. Secondly, if you want to use the power lines to provide your excess electricity to your neighbour, you have to pay the company that runs the poles and wires, which is the distribution company. And the models that they use are what's called the postage stamp network. So it costs as much to move electricity to your neighbour as it does to move it from the tip of Queensland to Tasmania. Okay? It's like, you know, when you buy a stamp, you pay for the amount, you put it on the envelope. It doesn't really matter where that letter's going to. It's a flat rate. It's calculated on the cost of the whole system. So if you're sending electricity next door, you're going to pay a lot for those electrons to go a few metres. Okay? So that has to change. There's this inability also to formalise costs and manage billings, and what if things go wrong, and you know, how do you manage that sort of system, which at the moment you leave to the retailer. But it's so attractive that people are starting to try and implement it now. My excess PV can be used by a neighbour. I could be able to use their battery, and we can cooperate to reduce our costs. So it's crazy to have 5 homes in a street drawing on the grid because they need energy at a particular time, and the other 5 homes on the grid producing energy, selling it back or having it taken back to the grid, when in fact they can cooperate and not use the grid at all for many hours. And there is a societal benefit to that too. So we can reduce our need from the grid and assist the wider grid as well if we can overcome the barriers to connecting up and managing cooperative community energy networks. And I guess diagrammatically this is the sort of thing that we're seeing. We have groups of, or in this case a single home, they have a PV system, they have a load, in other words some requirement for electricity that is changing, you know, every few minutes as appliances go on and off and things happen. They have a battery, there's a system here we've called a balancer, And we want to know how these systems will work together and how much they would then rely on or export to the grid. So we start developing mathematical models that adjust themselves on the basis of the ability of the PV panel to generate, the ability of the house to use its neighbour's battery, etc. And they quickly become, at least what we've found, is extremely complicated. This is an outcome of one of those models where we've looked at 9 homes, okay, labelled K1 to K9. What we see straight away, for example, K6 has a lot of energy or a lot of electricity going into it on average. Okay? So it clearly doesn't have a lot of local generation. K7, on the other hand, is sending a lot of its energy to other homes in the neighbourhood. K5 is a net consumer of energy. What else? I think that they are the main 2 producers. So what you start to see is there becomes a very, very complex network of energy flows, and to do it properly you need to put an economic value to that so that people are rewarded for using a resource or pay for it. Otherwise, without a cost involved, people tend to become unconcerned about excess usage. So we try and work out at what levels does it become economic to do this. When there is a cost for the battery, there's a cost for managing the whole system. And it turns out that in many cases it's much more economic to do it this way than it is to burn some more coal in a power station 200 kilometres away, ship it down transmission lines and provide it to home 5, when in fact home 7 is producing excess electricity 20 metres away. And that brings us to the Internet of Energy things, because to do that efficiently and low cost, you need to have intelligent systems that understand what's happening. What is my neighbour's PV panel doing? What is their load? What's the state of charge of any battery within a 10-kilometre radius of me that I could draw on? Now, up till a few years ago, it was prohibitively expensive to even think about doing that. In fact, a surprising thing that a distribution engineer once told me, he said, at the distribution level, this is the poles and wires in your street, he said, we have no feeling for what the voltage or the current is at that level. We don't measure it. He says, it's too expensive, we can't do it. He said, the only way we know there's been a failure is when people ring up and say, the lights have gone out. And then they send an engineer and they start testing from the top all the way down until they find the fault. Typically, it's, some switch has turned off or there's been an overload and it has to be reset. But at that local level, there is almost no intelligence whatsoever. At the high voltage level, it's very different. A lot of energy, a lot of monitoring, temperature measurements, power flows, everything done all the time. But at our level, it's not. So anyway, the Internet of Energy things. I think probably you've already come across the Internet of Things. Okay. Yes? No? Understand that? Yep. Okay. The Internet of Energy things are devices, sensors, communication systems that measure and talk about energy. They talk to each other, they take readings, they make the readings available to other systems, they provide this level of intelligence for a system that's so deeply going to be interconnected to make that work. Now, it's a good thing, but there's also a very, very serious hole or a downside in the Internet of Energy things, and that, of course, is security, cyber security. Once the power system becomes so deeply interconnected, there's going to be millions of ways for people to go in and try and hack the system. And we've already seen, there's not much talk about it, but we know there's been power systems that have been hacked in other countries. There's been an attempt in Australia. For whatever reason, people are tempted to go in and see whether they can create havoc. So there's a great upside to it, low cost, very efficient movement of information, very big challenge, how to manage the security of systems that are talking through a public internet system. And look, the tools are available, and I've got here often free. Right? A lot of the communication platforms, the calculation platforms have been developed in the open source community. This is the, where people develop software packages, for example, and make them available at no cost. You can take the code, you can improve it. Generally, you would then make it available to other people as well. Things like Firefox, right, the web browser, that's an open source project. It's developed by lots and lots of people, all doing little bits, making it publicly available for people to use. You don't have to pay for it. There's a thing called Node-RED. Anyone use or come across Node-RED? Yep, okay. So a couple of people have heard of it. Node-RED was actually developed by IBM a few years ago, and they open sourced it. So you can download the platform. It runs in your browser. And what it is, it's a very easy graphical way of connecting up sensors to the outside world. So, for example, if you have a system here that is measuring your energy consumption in your home, it's very easy to wire this up. That an output here would be to your Twitter account or your email or another device. And you basically set this up graphically, you deploy it, and then the system will work pretty much untouched, forever on. And I've recently had a play with this. I've got a system now which is measuring voltages and temperatures, etc., at different locations. And it's just basically sending out that information via email and to other systems who wait for it, get that information and make a decision. So the tools are there. I guess it's the high-level concept of how to use them that is still not clear to lots of people. So in the future, maybe the near future, maybe not so near, it would be conceivable, for example, that there would be an app related to something like the Uber platform, where every home that was part of this system would advertise, communicate its need for electricity, its ability to provide electricity if it had panels, the ability to store electricity if it had batteries, to a platform that then shared that information to other people. So my app, for example, would be able to go to this one and say, I'm looking for the lowest price electricity that I can get tonight. And the app would manage that and say, okay, well, look, where you live, there's 5 homes within a kilometre radius that have excess generation according to their Internet of Things device. And the app would then manage the bill. The electrons don't know where they're coming or going from, so we have to make the assumption that the energy flows from where it's generated to where it's needed. But that happens naturally anyway. An electricity system is much like a system of water. It will always tend to find the level that is the lowest energy. So if your neighbour is generating power through their PV, it's highly likely that if you need power, those electrons actually will find their way to your home, simply because of the ability of currents to flow to the lowest point. So it's potentially something that's going to happen. And of course, if this happens, then that again creates a huge level of uncertainty for the planners. Do the planners say, look, if this is going to happen, we may not need another power station to be built, ever? We don't know. What does the investor do? Investor thinks, look, I've been, investing in power infrastructure for the last decade or two. We make a good return. Am I going to take a risk, spend $1 billion on a power station, even if it's, a wind farm somewhere, and then find out in 10 years it's not going to be needed? So there's a lot of uncertainty that I guess people are starting to come to grips with as to where the system is going to need investment and where the use is going to come from. And one of the questions that we've looked at is how will local distributed power systems integrate with the national power grid? Okay, so we have this grid. We know there's big power stations far away. There's transmission lines bringing the power to us. At the small scale, we know it's manageable. It's almost ignorable. Okay, a few percent of photovoltaics on the roof in Sydney or Melbourne or Brisbane is not going to cause any grief. 15% of solar on roofs is going to start causing some grief. At least it may cause grief for some days or some hours of the day, some days of the year. One of the things that has got people worried is it's called the duck, right? It's a duck curve because it basically looks a little bit like a duck. Okay, there's the head and there's the tail. And what it shows is it shows the required energy from the grid for different hours of a day. Say, every day for a month, for example, but at the same time slot, it's overlain. So, for example, the 2012 and the 2013 actual requirement was here. So you can see 6 a.m. is a slight increase in the need of electricity from the grid. It drops towards the end of the day and then rises rapidly in the evening, which is very typical of a power system, that people come home, turn on the stove, lights, television, cook, etc., etc. So power goes up. But what they're finding is that with more and more solar power that's going to be used, during the day, there's going to be less and less need to take energy from the power system, from the grid, from those large remote power stations. But what happens when there is a large amount of solar generated in the middle of the day, and there's a big, you know, in the stomach of the duck, it's going down a lot. As the sun goes down, then the requirement to take energy from the grid rises extremely quickly. The more solar you have, the faster the change. And we know from experience that fast changing loads create problems because the generators always have to meet the demand. And if you can't turn the wick up on your gas plant or your coal plant or your nuclear power plant fast enough, then you're going to have a point where the frequency is going to collapse. So this duck curve has become a worry to planners. Yes, it's wonderful to have lots of solar. It's wonderful that you're getting a lot of zero emission, good quality electricity during the day. But towards the end of the day, people don't suddenly say, okay, the sun's going down, I won't turn on the television now, I'm not going to cook, I won't turn the lights on. People want to carry on with their lives as they always have. So the demand for electricity goes up just as the solar output drops. And this causes lots of problems for systems that only have a conventional system with a lot of solar. So these are big arguments for things like battery storage or other ways of managing this. Because if you can store that energy during the day and utilise it under the curve here, then you don't have this big challenge. So in California, for example, the planners have already started to mandate they have to have a certain amount of energy storage associated with their local network. And that's to avoid future problems like this. How will large-scale grid-connected battery storage affect the NEM operation? 5:30, should be wrapping up soon? Yep, okay. Well, we've looked at storage at small scale, community scale, and this large scale. If you could potentially design a battery plant that would attach to a big generator of some description. How is that going to affect things like the efficiency of the system? Because remember, every time we convert energy from one form to another, we have a loss. So in a battery system, it's the same. If you've got a loss of 10% every time you charge and discharge a battery, you could potentially increase the emissions of a system by adding energy storage. You might think, well, how is that possible? Well, it's possible because if you add storage that displaces a low emission source like gas and encourages a high emission source like coal, which would generate electricity at night, then you're actually going to increase the emissions of the system. Probably an unintended side effect. So we've had a close look at this and done some analysis. Basically, it required the solution, the simultaneous solution of a few 100 million equations. Because what we do is every 15 minutes, we look at the entire system, what every generator is doing, what the load is doing for that 15 minutes, what the battery system will be doing, what the wind power, what solar, and what everything else is doing for that 15 minutes. And we try and solve this equation for a period of a year. Okay? So it requires a simultaneous solution of lots and lots of equations. We use something called mixed integer linear programming. We've only been able to do it for a week. Okay? 1 week's worth of snapshot is as much as we can get computed without bringing down a high-performance supercomputer, okay? Because it just has so many equations to solve, it can't solve them. So we looked at this for 1 week in each of the seasons, you know, summer, autumn, spring, etc., to have a look. And this is I guess, a pictorial of the model. We divide the national electricity market into the regions. We know there are generators in the regions. We know there's storage there. We've put it there to simulate, to analyse. We know there's loads, and we know that the regions can send power to and from each other, as we saw this morning. They're continuously moving energy backwards and forwards, depending on generation, load and cost. So we try to solve this issue to see if we deploy large-scale battery systems, is it actually going to be a good thing for the current grid that we've got or not? The answer that we got was that yes, large-scale battery storage does help, and it helps because it allows the existing thermal generators to be more efficient, because, you know, they go up and down in terms of their output depending on the load. And for a thermal power station, a coal-fired power station, for example, it can only change its output at a certain rate. That rate depends on how fast the coal can actually be burnt and heat up the boiler and the steam developed and driven the turbine. And typically they can't move their output up and down very quickly. If the output, the load, is low at nights, coal-fired power stations don't want to turn off. You can't, you know, turning a coal-fired power station off is a very, very expensive thing, because the boiler then will cool down, and to restart it you might have to spend $100,000 on diesel fuel, and it'll take maybe 12 hours for it to get back up to temperature. You can't do it too quickly because the expansion and contraction materials will wear it. So what we found was that having batteries to take up the slack and to provide the excess at a high frequency enabled the thermal generators to operate much more efficiently. They didn't have to stay partly loaded. They didn't have to turn on from cold. They had less cold and warm starts. So the batteries actually helped the thermal power generators as well as the renewables. And it did lower the greenhouse gas emissions. Okay? So we were very pleased to see that, at least in our simulation. So to conclude, you know, where to focus? Where should we focus? Where do you think you might want to focus? I mean, this is a global challenge. It's a technology, social, community challenge. We're looking at battery chemistry, and lots of groups are looking at battery chemistry. Battery chemistry's got a long way to go. Currently, you know, lithium-ion systems are the best. They can be improved a lot. Okay? Battery chemistry is a good place to look. Energy modelling and simulation, especially big data, and this is one of the exciting things and also the really challenging things is when you start to try to simulate a power system like this. The amount of data that you have to handle is just massive, you know, terabytes of data. So you really need to understand how can you capture that, how can you analyse it, how can you save it, how can you work with it. So big data is something that we have to come to grips with. Machine-to-machine communication is very important. And with this comes machine learning. And what we can see now that there are systems that can enable us to learn, or the machine to learn, to look at the historical use of electricity, for example, from a business, from a city, from a network, and to learn so that it can predict how much energy is going to be required on a particular hour of a particular day forward. It could be tomorrow, it could be next week, it could be next year. But machine learning has enabled us to say, okay, well, because we know on a Thursday, historically there's been a lot of energy consumed at this university because there's more classes on a Thursday, there's more use of electrical equipment, Mondays and Tuesdays not as much. We're able to learn and to use that forecast in our models. Businesses do the same thing. So machine learning is becoming a very valuable tool for us. I think coding and open source platforms is going to be an integral part of the way that the community in general, the engineering scientific community is going to handle developing solutions to the future grid. Just thinking about how cell phones changed land telephony, and a colleague of mine has a terrific anecdote. He said, if you brought back Alexander Graham Bell today and had a look at how we communicate via phone, he would be totally blown away. Cellular networks, everything that up to landlines, he would understand. But computer control systems with Wi-Fi, mixing voice signals with data, he would just say, look, this is something that's completely different. If you brought back Alexander Thomas Edison today, who developed the original power system, he would understand everything. He could say, yeah, I can see there's a coal-fired power station, there's a transformer, power lines, lights, everything else. I understand the system. The power system hasn't gone through that disruptive technological change that the communication and phone systems have. But it's very close. I think it's going to be, the next 5 years are going to see the technological pressure on the electricity supply system to change. Now, this is a very, very big system, a very expensive system, and that change is going to be very disruptive and painful for a lot of players. So my suggestion is develop your deep quantitative skills, physics, engineering, maths, computer science, because we are going to need people like you to help solve this problem. Thank you.